Hello, this is Dr. Bauer, and we're going to look at an introduction to propositional logic, section 1.1 in Rosen's text. But first, let me just mention I have on the PowerPoint here, and it's also in Blackboard in week 1, a link to some videos by another professor, Professor Cerna. A retired gentleman, but he still has a tutoring center, but he has these videos up for discrete math, and you can follow that link and watch his videos on propositional logic. First of all, what is a proposition? Well, a proposition is simply a statement that's either true or false, but not both. In other words, you can clearly tell whether that statement is true or whether that statement is false. Now, page 2 in the text gives examples or non-examples of propositions. Let me bring up the text real quick. This is page 2 of the text, and example 1 mentions Washington, D.C. is the capital of the United States of America. Now, that's clearly true. Toronto is the capital of Canada. That's false. Toronto is not the capital of Canada. Toronto is the capital of Ontario, but not of all of Canada. 1 plus 1 equals 2, obviously true. 2 plus 2 equals 3, obviously false. But those are all propositions. But down here in example 2, it says, consider the following sentences. What time is it? Now, you can't tell if that's true or false. It's just a question. Read this carefully. That's just a command to someone to do something. That's not true or false. Also, x plus 1 equals 2. Now, you can't tell if that's true or false because you don't know what x is. So that's not a proposition. Or x plus y equals z. You don't know. Now, these are called propositional variables, but essentially we cannot tell if these statements are true or false. Okay, I'm trying to bring up the slideshow. All right. Now, in the next slide, it talks about the negation of a proposition, and we denote it with this symbol that looks, goes over and then down, but it's like a negative sign, and it's just means the negation of the statement, or not that statement, or it is not the case that that statement is true. So some examples would be if you said, Atlanta is the capital of Georgia. If the opposite of that, or the negation of that statement, is Atlanta is not the capital of Georgia. Now, a negation will have an opposite truth value. So if the original statement is true, the negation will be false. But if the original statement was false, then the negation will be true. Now the proposition P and Q is taking two statements P and Q and joining them with what we call a conjunction statement and, or the conjunction operator and. So when I say, Atlanta is the capital of Georgia and Mobile is the capital of Alabama, I'm saying both of those statements are true. Now that is not true because I don't think Mobile is the capital of Alabama. So it's got to be the case that both statements are true for the whole compound conjunction statement to be true. So as it says in point B on the PowerPoint, P and Q, which is denoted by an upside down V, it's only true if both P and Q are true, but it's false if either one of those is false. All right, now P or Q, that's item C in the slide, is denoted with the V symbol. So P and then what looks like a V and then Q, we would say P or Q, is true when either P is true or Q is true or when both are true. It's only false when both P and Q are false. So if I make the statement, Athens is the capital of Georgia, or Mobile is the capital of Alabama, that's false, because neither of those statements are true. But if just one of them is true, then the or situation, called the disjunction, would be true. Then D talks about the exclusive or of P and Q, denoted by P and then a plus sign with a circle around it, Q. It's the proposition that is true when exactly one of P or true or Q is true, but is false otherwise. So it's when exactly one, only one of them is true. All right. Now, if I made the statement to my granddaughter, whose name is Lexi, if I said, I will either take you to the park or I'll take you to McDonald's, but not both, that would be the exclusive or. But if I said, I will either take you to the park or to McDonald's, then I'm just using the regular or disjunction situation. So in the case of if I just said I'll either take you to the park or to McDonald's, then if I did one of them, if I took her to the park, or if I took her to the McDonald's, or if I did both of them, I would still be telling the truth. So that statement, that or statement, would still be true. But if I was using the exclusive or, where I said, I will either take you to the park or to McDonald's, but not both, that's the exclusive or. So if I did both, that would be false. I would be not telling the truth. Now let's look at truth tables for these statements. There's a YouTube video also you can watch that I've got a link for here in the PowerPoint, and you can, I'm going to post the PowerPoint. You can link to that and watch video tapes on this if you still don't understand, but I'm going to fill it. We're going to fill in some here. So if I have the truth table P and then not P, so I'm doing a truth table for this last thing, the column here, not P. Now, in the case of when you only have one proposition, P, there's only two options. It's either true or it's false. So that's why I only have 2 rows to this truth table. So I've got either true or false. Now, what did we say about the negation of P? Well, the negation, if P is true, the negation would be false. All right. Now, if P is false, then negation would be true. So a negation, this not P situation, always does the opposite of whatever P is. All right, now look at table 2. Now table 2 has 3 things. It has the and situation, which is this third column here, and it has the or situation, which is the fourth column, and it has the exclusive or. So we're really doing 3 truth tables here. Now, since we have 2 statements, P and Q, then we need actually 4 rows. The way to tell how many rows you need is you take the number 2 and you take it to the power of how many propositions you have. So if I have P and Q, I've got 2 propositions, so I'm going to take 2 to the second power, and that, of course, equals 4. All right, so we're going to need 4 rows. Now, you make the first 2 rows true for P, the last 2 rows false. So it's always half of the rows true, half of the rows false. And then you subdivide each half for the second column. And so now there's only 2 in the first half. So I'm going to alternate true, false, and then in the second half, true, false. We'll look at a table that has 8 rows, and so the first 4 will be true for the P, and the last 4 will be true for the false, or will be false for the P, but then you'll alternate 2 and 2, 2 and 2, 2 and 2, 2 and 2, and then you'll alternate. We'll look at this when we get to the 8-row table. All right, now what does it take for and to be true? Well, it takes both of them to be true. So you see that both of them are true in the first case, so this will be true. But in the second row, both of them are not true, so that's going to be false. And the third row, both of them are not true. And in the last case, both of them are not true. So the only row where it's true for and is when both are true. Now in the next situation, we have an or situation. This is an or situation, because that symbol V means or. The one we just did was the and. Now or, we just need one of them to be true, and so that's what we have. We have at least one of them to be true in the first row. In the second row, we also have at least one to be true, so that's true. In the third row, we have at least one of them is true. And in the last case, we don't have either of them to be true, so it's false. In the exclusive or situation, you could call it the XOR, exclusive or situation, this last case. It's exactly one has to be true. Now in the first row, we don't have exactly one, we have both of them. That's not exactly one, so that's going to be false. But in the second row, we do have exactly one, and in the third row, we have exactly one being true. But in the last case, we do not have one, so it's not exactly one to be true. So these are the truth values for XOR given these truth values for P and Q. Let's look at a conditional proposition. In implication, P implies Q. That's how we say that. P arrow Q, also called a conditional proposition, is the proposition that is true in all cases except where P is true but Q is false. P implies Q is an implication that essentially means that if P, the hypothesis, or called the premise, is true, then Q, the conclusion or consequence, will be true. Now, this would be an analogy if I said this to my granddaughter. Lexi, if you clean your room, then, or if you pick up the toys, let's say that because she doesn't live with me. If you pick up your toys that you were playing with, then we'll go to the park. Okay, so when would I be lying and when would I be telling the truth? So if she picks up the toys and I take her to the park, obviously I'm telling the truth. So that would be if P is true and Q is true. But in the case of if you pick up the toys, then I'll go to the park. If she picked up the toys, but it was false that I took her to the park, then that's when I would be lying. So my statement, if P then Q, would be false. So that's what I'm talking about here. It's true in all cases except where P is true but Q is false. Now what happens if she doesn't pick up her toys? If we go to the park, am I still lying? No. I'm probably spoiling her, but I'm not lying. If she did not pick up her toys, but I still took her to the park, my statement was still true. Maybe something happened. Maybe she got sick, or maybe she something happened and someone else picked up the toys. I don't know. But my statement would not be false if I had said, if you pick up your toys, I'll take you to the park, and she never picked up the toys, but I took her to the park anyway. Or if I didn't take her to the park. Either way, if she doesn't pick up her toys, if P is false, then the statement P then Q still is true. So that's what it says in yellow here. If P is false, no claim about Q is made. So the implication P implies Q is still true no matter what Q is. All right? Now, students have trouble sometimes when it doesn't say if P then Q in that type of format, translating from an English sentence into logical symbolism. So I've given this list down at the bottom of the slide that says all of the following also mean P implies Q. So if you see P implies Q, that format, or P is sufficient for Q, or Q is true whenever P is true, which is like saying Q is true if P. So the word if or whenever is sort of in front of P. Or if it says P only if Q. Now that's a little bit confusing because the if is in front of the Q, but it's not just if, it's only if. So whenever you see P only if Q, that really means if P, then Q. It's kind of a weird one. And then second to last, Q is necessary for P. So that one's another one you kind of switch around. That means if P, then Q. Or if it's stated Q if P. Now that one's more logical because the word if is right in front of the P. So of course it would be if P, then Q. So whenever you have sentences such as, okay, looking at this one here, P is sufficient for Q. If I said, Lexi picking up her toys is sufficient for me to take her to the park. That would mean that basically if she picked up her toys, then I would take her to the park. But if I said going to the park, to go to the park, it's necessary that she picks up her toys. That would mean, oh, I'm sorry, no. I'm getting confused. Going to the park is necessary for Lexi to pick up her toys. Would mean that if she picked up her toys, then she would get to go to the park, or we would go to the park. Okay, moving on. Special condition propositions. Consider the statements. If it is raining, then there are clouds in the sky. Now, most people would agree with that statement, right? If it is raining, then there are clouds in the sky. Let's symbolize it by R implies C. So if it is raining, then there are clouds in the sky. So there's some special statements. There's the converse, there's the inverse, and then there's a contrapositive. The converse, you just switch around the P and the Q. So if the statement is if P, then Q, then this would be if Q, then P. So in the case of if it's raining, then there are clouds in the sky, the converse of if it's raining, then clouds in the sky is if there are clouds in the sky, then it's raining, which is obviously not true. For the inverse of P, then Q, is if not P, then not Q. Okay, so not having P true implies not having Q true. So in the case of the inverse of if it's raining, then there are clouds in the sky, it's if it's not raining, then there are not clouds in the sky. which, if you think about it, that's not true, is it? And the same thing with the converse. So the converse and the inverse are not necessarily true if the original statement is true. Okay? Now look at the contrapositive. The contrapositive of if P then Q is if not Q, then not P. Now in the case of if it's raining, then there are clouds in the sky, that would be if there are no clouds in the sky, then it's not raining. Now, is that true? If there's no clouds in the sky, then it's not raining? Yeah, pretty much that's true. So you can see that if the original statement is true, then the contrapositive is true. Okay? So what did we do to create the contrapositive? We not only switched around the P and the Q, but we negated both of them. So if you switch around the order of the P and the Q and you negate them, you create the contrapositive, which is what we call logically equivalent to the original statement. Okay, which in this case be if there are no clouds in the sky, then there's no rain, which most people would accept to be true. I'm just going to go on. All right, so we're going to talk now about biconditionals and more truth tables. A biconditional, P, and then you have a double arrow Q, is the proposition that is true when P and Q have identical truth values and is false otherwise. So in other words, if both P and Q are true, then this biconditional is going to be true. Or if both P and Q is false, then the biconditional will be true. So it basically tells if P and Q have the same truth value. Okay. Now we can write it in English words using the phrase if and only if. So if you see P if and only if Q, or it's abbreviated PIFF-Q, that's really called the biconditional. Now why is it called a biconditional? Because it's basically saying if P is true, then Q is going to be true, or the other way around. If Q is true, then P is true. All right? So if we were to all right, so now we're going to look at filling in this conditional truth table. A conditional is just one direction. If P, then Q. So we said that if P is true, then Q is true, then the whole conditional is true. But we said also that if P is true but Q is false, then that's the time when a conditional, P implies Q, is false. Like when I said that my granddaughter, if I said to my granddaughter, if you pick up your toys, we'll go to the park. If I did not take her to the park, but she picked up her toy, in other words, P is true, but Q is false. That's when I would be lying, and so my statement would be false. But if she didn't pick up her toys, it doesn't matter what happens after that. In both cases, my statement was true. Whether we went to the park or not, my statement was still true. The only time it would be false is when she picked up the toys, but I didn't take her to the park. Now, in the case of a biconditional truth table, where we have this this symbol with the double arrows, which means both ways. It goes both ways. If they're both true, then that's going to be true. Or if they're both false, it's going to be true. But when they're different truth values, where one's true, one's false, that's going to be false. Or that's going to be, in the case of the third row, that's going to be false. Okay? So the biconditional is true in the first two, or the first and the last rows of a truth table that's made in the standard way. All right. All right. Going on to the next slide, let's look at the truth table for the inverse statement. The inverse statement. Now, the inverse statement is this statement here where you've just taken the P arrow Q statement, but you've negated both of those statements. Notice we put a not in front of them. So that's the inverse truth table, inverse statement. Now, first, you need, whenever you have a statement involving a not, of the negation of a statement, you need to make a column for that negation. So I have a negation of P, so I'm going to need a negate P column, and a negation of Q, so I'm going to need that column. Now, all you have to do is take and do the opposite of the P column to get the not P column. So I'm taking the first column and negating all the values in the first column. So instead of true, true, false, false, it's false, false, true, true. And then the Q column is true, false, true, false. The negation of that would be false, true, and then false, true. Okay, so you basically negate the P and the Q columns. All right, then we are doing the implication, an if-then statement. Now, when is the if-then statement false? Well, it's only false in this case right here, where the first thing is true, but the second thing is false. So notice we're not using the P and Q columns, we're using the negation columns. But the if-then that we create from these negations is only false when it's true for the beginning statement, but it's false for the then statement. All the other times, it's true. So that's the completed truth table for the inverse statement. The contrapositive truth table, okay? Now, we need, for this contrapositive, the negation of Q, the negation of P, and then we need to do the implication of that. So notice I'm going to put the negation of Q first, so it's in the same order as the statement is, the contrapositive, okay? And realize that the contrapositive both switched the P and the Q around and negated them. So that's why the order is not Q implies not P. So in the case of not Q, we're going to do the negation of the Q column. So we're going to say false, true, false, true. And then we'll do the negation of the P column. So instead of true, true, false, false, we'll have false, false, true, true. Okay, so now we have the negation columns. Now we'll do the implication, the if-then, or the conditional statement that we get using these two columns. Now, when is this type of conditional false? It's only in the case when the first thing is true, but the second thing is false. So that's false, but all the other times it's true. All the other times it's true. So this is the truth table for the contrapositive. Okay. Now you'll notice that the truth table for the contrapositive is really going to be the same as the truth table for the conditional P then Q. Because the conditional P then Q would be false in the case when the first thing is true and the second thing is false, which is what we encountered here. It was false in that case. So that shows that the original statement P implies Q and the contrapositive, not Q implies not P, are logically equivalent. Okay. Now, moving on to the next oops, next slide. Truth tables of a compound proposition. Now what this is talking about is some complicated compound propositions such as I've circled here. To do the truth table for that, we need to think about the parts of it. So we want to have our final column be that, but what are the parts of it? Well, you see in parentheses, I've got this part here, which I made a column for that. And I also made a column for the other item in parentheses. But inside that first item in parentheses, I have a not A. Okay, so I need also a not situation here to go along with this not. All right, so then I'm going to negate the A column. So I'll start off and go false, false. Oops. And true, true. And then I have not A and B. So I'm going to look at the not A and the B column. When is and, this is the symbol for and, when is and true? Well, it's only true when both are true, which happens here where both are true. All the other times it's false. Okay, then I look at the A or B situation. A or B means we're going to look at the first two columns, and when is A or B true? When either the A is true or the B is true, but it would be false when they're both false. Okay. All right. So now we can look at the combined statement, and this is a negation. I mean, this is a conditional implication. So I'm going to look at the fourth column, which is the first parentheses, and the fifth column, which is the second parentheses, and do implication. Now, when the first thing is false, then the implication is still true. So in the first two rows, since the first thing is false, that's going to be true. And the third row has both true, so that's going to be true. And the last row has both false, so that's going to be true. So in that case, it looks like this statement is always true. All right. Now, when a statement is always true for all the values of the propositions that are in the statement, then that's called a tautology. Okay, so it's always true no matter what the values of the original propositions. Okay, then you might have wondered, in our last slide we had a real complicated expression, this expression that you see at the end, the last column of the table. Why did we have to have parentheses there? Is there like an order of operations for logical symbols? And the answer is yes. There is an order of operations. And so just like in math, algebra, there's parentheses, exponents, please excuse my dear Aunt Sally, all of that. Well, in the same way, we have an order of logical statements. So parentheses are always done first, negations, then conjunctions and disjunctions, implications, then biconditionals. So you can tell when you need parentheses and when you don't. If you're okay with it doing it in that order, then you don't need parentheses. But if you ever have to make maybe a conjunction go before negation, or implication go before a conjunction or something like that, then you need parentheses, okay? So that's the precedent of logical operations. And then the last item here talks about logic in bit operations. Now, bit operations has to do with the inner workings of a computer in the microprocessor. And in the microprocessor, often it takes when a electrical circuit is on, and it interprets that with another electrical circuit, and then makes a decision about whether it's going to open or close another electrical circuit. And so imagine the ones representing the circuit being on, and the zeros represent the circuit being off. Well, this is like true and false. True being the circuit is on, false being the circuit is off. So this refers really to the inner workings of a computer all the way down to the bits, the ones and the zeros. So as you can see in this table, the third column, and x and y, and is done when both of them are true. So when both are ones, this will be a 1. But all the other times it's false, so it's a 0. Now, or the fourth column here is done when either the first or the second or both are true. So in the case when both are ones, then this is going to be 1. When in the second and the third rows of the columns, you see that they both ended up with a 1 also, because at least one of them is a 1. But in the last row, it's a 0 because we don't have at least one being true. XOR, you have to have exactly 1. So if both are on or both are true, then it's going to be false. But if one is true and one is false, then it's going to be true. In the last column, you have the implication. X implies Y. So this is talking about if X is true, then Y is true. Now that whole statement is true in the case when both are true, but it's false if the first thing, the X, is a 1 and the Y is a 0. So that's the whole statement. X implies Y would be false. But the other times when X is 0, it's going to be true or on or 1. You can look at it various ways. So here's an example showing you what do you do if you have a long expression of binary numbers, bits. All right. So let's say we have this row and this row, and then a bar to indicate those are 2 rows that we're going to apply the bitwise AND or the bitwise OR the bitwise XOR to. So the bitwise AND is really going to look at it bit by bit. So look at the first little column of ones and zeros. 1 and a 0. Well, and you have to have both being true. So that's going to be false. That's going to be false. Same thing in the next column. But in the third column, you have both of them with a 1, so that's going to be a 1. Same thing with the fourth column. Both of them with a 1, so you have a 1. But in the case of the next 3, you don't have both of them being on. In the column number 8, I guess it is, you have both of them with a 1, so it's going to be a 1. But then you don't have that in the other ones. Now the OR situation is either one or the other. So you can see that you have a lot more ones than zeros. The only time when it's not is when both of them are 0, then you have a 0. In the case of this, the 5th column or the 7th column. And then the XOR you have about as many ones and zeros, ones as in zeros, because it's going to be when exactly one are true. So in the case of the first column, you have exactly one being true, so that's one. Same thing with the second column, exactly one of them is true. But in the third column, you don't have exactly one, you have two being true, so that's false. So you can look at this, all right? There's also examples in the textbook for this. All right, so that's the rest of the that's the notes for section 1.1. You can either try the homework on this and master the homework for this section, which I would recommend, and then watch the video for section 1.2, or you can keep watching more videos and then do your homework all together. You know, perhaps something in section 1.2's video will help you understand the section 1.1, but either way you want to do it, you know, after you get done watching the videos, you should take the exit survey on this video material. All right. Thank you. Bye.